So, hello and welcome. Good morning, students. So, let us start today's lecture, MA415 Algebra. Okay, and this is the lecture number 17. Okay, now recall that we were discussing about nilpotent group. Okay, and we proved that nilpotent group, several characterization of nilpotent group, right? In fact, so what we proved that if G be an nilpotent group, then it has many characterizations like G is nilpotent. Okay, so I already assumed that this is some P1 power alpha 1 dot finite nilpotent group Pk power alpha k. Okay, then this is equivalent to saying that every proper subgroup of G is properly contained in G. So that is, if H is a proper subgroup of G, this implies H is a proper subgroup of normalizer of H in G, right? And then every PCLO subgroups, so they are not subgroup of G, right? For all Pi belongs to side group PIG. And then G can be written as product of direct product of this P1, P2, Pk, and then 4. They're all equivalent, and then if you have a divisor D, so D divides order of G, then you have null subgroup of the same, right? So G has a normal subgroup of order D. These are all equivalent, okay? And yeah, so immediately we can have some corollary. So let me write down the corollary, immediate corollary. So every finite abelian group what happened for abelian group is the direct product of its silo subgroups, right? Silo subgroups. And proof is obvious because abelian groups are nilpotent group of order nilpotence class 1, and we know that for nilpotent group these are product of silo subgroup. So abelian groups are nilpotent of class nilpotency class 1, okay? And for nilpotent group we already know that then number 4 characterization, they are direct product of P silo subgroups. So this is actually part of something called fundamental theorem of finite abelian groups, the first part. Then you can write down abelian group product of P groups, because these silo subgroups are all P groups, right? And each P silo subgroups also can be written as a product of some product of Z mod of Pz, okay? P power Z. That I will come later, maybe we will give later a proof, okay? Okay, so this is a straightforward proof. Yeah, so but now we are going to give one of the most fundamental theorem, and this theorem tells you that a finite group is nilpotent if and only if, what happens if and only if every maximal ideals, maximal subgroups is normal subgroup. Okay. Yeah. So we know that for nilpotent group, maximal subgroup of normal subgroup, right? But the converse is also true, right? So let me give a proof. Yeah. So there are two parts. And for one part it is straightforward, but for the second part I need the okay, so let me start with the proof and then I will tell you the proof. So so let G be a finite nilpotent group and yeah, maximal subgroup M be a maximal. See, I'm saying a maximal. So what does that mean? That means it need not be unique. Maximal subgroup of G. Okay. So the one of the property of nilpotent group tells you that whenever you have a normal subgroup, whenever you have a, see, what does that mean? That is so see, M is a proper subgroup of G and M does not contain in any proper subgroup of G, right? This is the meaning of maximal proper subgroup of G, right? Yeah, but you recall that property of property number say 2, which tells that whenever you have whenever you have a proper subgroup, then it is always inside the normalizer of that, right? So thus you can say that this M is always inside this, okay, and it must be equal to G as M is maximal, right? Otherwise, if it is not equal to G, then M cannot be maximal. That is the contradiction. So M this normalizer of M of G equal to G implies M is normal subgroup to G, right? So this part is almost obvious. Now we need to prove the converse is also important. True. Converse is the most important part. That suppose you have a finite groups and you know that every maximal subgroup is normal, then the group must be nilpotent group. Okay. Now how do we prove this kind of statement? To prove this kind of statement, we need a very important to prove converse. To prove the converse part, we need something very important, lemma or something. We need something called frattini's argument. So I need to first tell what is this frattini's argument. This is very classical and famous argument, famous lemma. Okay. Now let me tell you what is this frattini's argument or this lemma. Okay. So and then you will understand the proof converse part. Okay. Uh, so yeah, so here so frattini's argument. So what does frattini's argument? So this is a lemma that tells you that if you have a finite groups and a null subgroup of that thing, so let me write down properly. So let G be a finite group and H be a null subgroup of G. Okay, and also let P be a P-silo subgroup, subgroup of H. Okay, not G, H. Then what happened? Then G is the actually internal direct product of this the normalizer of this P inside G times H. Okay. So so what does that mean? That means okay. So that means every element of G can be written as a direct product of element from H and the normalizer of P in G. Okay, this is the meaning of that. Okay. So how do you prove this kind of statement? So okay, so let me first give a proof of this frattini's argument, then so proof of frattini's argument. Okay, so what is given? Given that H is a normal subgroup of G and P is inside this silo H. Okay, now for any G belongs to G, what happened? Let me first write down GPG inverse. So how does it look like GPG inverse? GPG inverse will be again a subgroup, and this is subgroup of GH G inverse, right? Because P is a subgroup of G. P is a subgroup of H also, so GPG inverse inside D, but H is normal, so this is H, right? This is H. So what does that mean? That means GP G inverse is a subgroup of H. Okay, and order of GP G inverse also same order of P. So what does that mean? So that means thus GP G inverse is a silo subgroup of H, right? What about P-silo subgroup? We can write down P-silo subgroup of H, right? But you already know that every P-silo subgroups is every P-silo subgroup of any group, they are actually conjugate to each other, right? So what does that mean? That means that is, so this GPG inverse is actually nothing but some HP H inverse for some H belongs to H, right? This is a P-silo subgroup of H, but every P-silo subgroup of H is of this form, right? And what does that mean? So this means that this implies that okay, so G inverse. Okay, so let me just write down how I am writing this. So I'm writing H later, right? Okay, no problem. So then that means, so you just multiply both sides by G inverse, so you have G inverse H P, and then you have G inverse H whole inverse, right? That is equal to P, right? So G inverse this equal to P. Okay. Okay. So what does that mean? That means G inverse H normalizes P, right? This is the meaning that this implies that G inverse of H belongs to normalizer of P in G, right? This normalizes this. Okay. Yeah, I think I need to start with the other way. Then it will be easy. Yeah, I think this is no problem. Okay, so mhm. Okay, so yeah, I think the proof should be start the other way. So let me start with G inverse, and then here I let me put this, 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 okay, this, and G inverse first. G inverse, G inverse, G inverse, G inverse, G inverse. This will be easier than here also. So this is G inverse, and then this is not, this is not, this is not. So yes, yeah. So now G inverse PH will be something of the form H inverse this, and hence it will be multiplied by G, then G H inverse P will be G H inverse whole inverse, right? Because G H inverse whole inverse means nothing but H G inverse, that will be here, right? You multiply by both sides, and hence what happens? Hence G H inverse will be element of the normalizer of P in G, right? And hence G belongs to normalizer of P into H, right? This is what we want. See, every element of G is of this form. Okay, so any element of G can be written as a element from normalizer of P in G into element of H, and thus G is nothing but this normalizer of this into H. This is true for if for all G belongs to G. This statement. Okay, that's why you have. So Frattini's argument tells you that whenever, what is the importance of this argument? So whenever you have a normal subgroup and a pixel subgroup, then you can generate the full group using the normal subgroup and the normalizer of that pixel subgroup inside G, right? Okay. So now with the help of this, we will complete the proof of that our main theorem. So that converse part. Okay. So proof of the converse part, right? So what I need to prove? I need to prove that if G be a group where a finite group where every maximal subgroup is normal subgroup, then G is nilpotent group, right? So let us assume that every maximal subgroup of G is normal. Let's assume that, okay. And then we need to we need to prove that G is nilpotent. But to prove G is nilpotent, there are several criteria, right? So we'll prove that every PCLO subgroup is normal subgroup, and then done. That was, remember, that was one of the criteria to prove G is a nilpotent group, right? So so to prove that, so let P be a PCLO subgroup, PCLO subgroup of G. Okay, and what we need to prove? We need to prove that P is not subgroup of G, right? And if P is not subgroup of G, then this P is arbitrary. So I chose arbitrary subgroup, and I will show that any arbitrary PCL subgroup is not subgroup, right? So so what happens? So if this P is normal, then nothing to prove, right? Nothing to prove. Nothing to prove. If um, P is not normal, okay, then what happens? Then you choose um, you choose the maximal subgroup of the containing P, containing this. Okay, so if P is not normal, but you know that what? You know that P is sitting inside this normalizer of P in G, right? P is sitting inside this, and you choose let M be a maximal subgroup of G, containing this this normalizer of P sitting inside this, and this is this. Okay, that is possible because every subgroup is always sitting inside some maximal subgroup, right? And the proof is simple. You have to use Jones lemma to prove this thing. Okay. So now, so what does that mean? So we know that M is so the P is sitting inside this normalizer of P in G, and this is sitting inside M, and M is in also subgroup of G because it is hypothesis. I assume that every normal subgroup is every maximal subgroup is normal subgroup, right? So this is we know that, right? Then what Frattini's argument tells you? The now Frattini's argument tells you that this is normal, and this is a PCLO subgroup, right? This is P belongs to CLO P of M, and M is normal subgroup of G, then by Frattini's argument, what happened? Frattini's argument tells you that G is nothing but, you can write down as this. So we call that, yeah. So G can write as the normalizer of this into H, by H equal to M here, right? So normalizer of P in G into M, right? So you can write down G in terms of this. Okay, so now again you, so this is one part. Okay, now again you know that normalizer of P, this is how you choose, that is inside the maximal subgroup M, right? So what does that mean? That means this portion is inside already M, and if you take the subgroup, the product thing, then this must be inside M, right? Because so if you take a product of element of M and M, so this is already so element from for any for, okay, so let me write down for any. So if you choose any this is also inside M, so any such product is element of M, right? But this is not possible because M is proper subgroup of G by definition. So this is a contradiction. This is a contradiction, right? This is not possible. You are showing that G is inside the maximal subgroup, but it cannot be possible because maximal subgroups are always proper subgroups, right? So what does that mean? That means P is always not subgroup of G. This is the meaning of the statement. So what does that mean? Every normal subgroup, every PCL subgroup is normal subgroup of G, and thus G is nilpotent. Nilpotent. Okay. Yeah. So this is one part of our discussion. Now we can also study this nilpotent group using something called lower central series like upper central series. But here we need to introduce some new idea and definition. So let me define those things properly first. So let me define. Okay, so this is called commutators. Okay. So let us define it. Okay, so let G be like any group, and you choose some element, say x, y belongs to G. Okay, whatever, and you choose some any subset of G, whatever you choose. Okay, so definition one, that we define this bracket x, y by this symbol x inverse, y inverse, x, y, and this is called the commutator of x and y. Okay. Similarly, for any subset A and B, we define this as the subgroup generated by the commutator of AB, such that A belongs to A and B belongs to B. So you choose these commutators and take the smallest subgroup generated by this, and that will be this symbol, right? And number 3 is very important. So we define G dash is nothing but the commutator of G. G, what does that mean? That means this is the subgroup generated by all the commutators xy, such that xy belongs to G. Okay, and this subgroup is called the commutator subgroup or derived subgroup of G. Okay, so this derived subgroup is very important subject, and it will play a very important role also many places. Now let me give some of the properties of commutators before we go to the nilpotentness of a group using this. Okay, so properties. So property number 1. So suppose you have this x, y. So these are all given to me, right? So and you have some h subgroup of these. So I can write down x, y is always y, x, and then commutator of x, y. Okay. So in particular, x, x and y commute with each other if and only if this commutator of xy equal to 1, right? Now proof is simple. I mean, this is nothing to prove, but let me just give you the simple proof. So you write down xy commutator. This is x inverse, y inverse, x, y, and hence if you multiply the inverse of x and y, then you will have xy equal to yx commutator of xy, right? Now if when x commutes with y, then what happens? Then you see that um, this xy become yx, so that is identity, so it become identity, right? So xy equal to yx implied by what? Implied by x inverse, y inverse, xy equal to 1. This is also if and only the commutator is equal to 1, right? So what we claim, that is also already also true. Okay, so if two elements commutes, then if and only the commutator is 1, right? So you can for commutator groups, what you can say? You can say that a group is abelian group. So G dash G. So note that A group G is okay. For any group G is abelian if and only G dash is identity subgroup, right? Yeah, so G dash means the commutator subgroup, like this thing. Okay, so now property number 2, it tells you that whenever if you have a normal subgroup, okay, that means that if and only it is of this form, the commutator of H in G is always inside H. Okay, and proof is what? So proof is also simple here. So this is also if and only portion. So what does that mean? So G is normal subgroup of G. What does that mean? If and only uh, G inverse belongs to H belongs to H for all H belongs to H and G belongs to G, right? But this means what? This means if and only um, this is so now you multiply by okay, or maybe I can write down by this way, that is much better. uh, G inverse H G inside H for all, and so if you multiply by H both sides, then what happens? H inverse is H inverse G inverse H G belongs to H, right? For all H belongs to H and G belongs to G. But what is this? This is nothing but commutator, right? Commutator of H and G. So that is belongs to H for all H belongs to H and G belongs to G. This is all if and only condition. So what does that mean? That if and only the subgroup generated by H and G, this is inside H. Okay, so this is if and only. So I am not say I prove both sides together. So this is if and only this is true. Clear? So this is one important observation. Another important observation is that these commutator subgroup, direct subgroup is always a characteristic subgroup. Okay, so 3. So G dash is a characteristic subgroup of G, and not only that, and the quotient is abelian. G mod G dash is abelian. Okay. Now, how to prove this kind of statement? So that means, see, so you need to first check what happened under an automorphism. So you start with automorphism, say, uh, so suppose if I belongs to automorphism, any automorphism of G, right? Now, what does phi do with the commutators? So if I which acting on any commutators, okay, how does it act? So it is phi of x inverse y inverse xy, which is nothing but phi of phi is a automorphism, right? So it's a homomorphism. So phi of x inverse, phi of y inverse, phi of x, and phi of y, right? And what does that mean? That means that it is nothing but equal to phi of x whole inverse, phi of y whole inverse, phi of x, phi of y. And what is this? This is nothing but the commutator of phi x, phi y, right? So what we prove? We prove that this is phi of commutators is nothing but commutator of the image of the commutators is nothing but the commutator of the image of the phi, right? So what does that mean? That means whenever phi um, uh, whenever phi mapping to a the commutator groups G dash, so what does that does do? So the element of G dash is of the form these commutators, but the image will be what? Image will be of this form, but they are also inside the commutator, right? Say phi x and phi y is again element of G, so image will be always sitting inside G dash, right? So thus G dash is invariant under 5 under any automorphism, right? So G dash is characteristics subgroup of G. Okay. Now, how to prove is abelian? So, what does that mean? So now we need to prove what? We need to prove G mod G dash is abelian, right? That we need to prove. Now, how to prove G mod G dash is abelian? So, let you choose two elements. So what will be the element of this? So, it will be of the form X G dash, Y G dash belongs to G mod G dash, two elements. Now let us check whether the commutes or not, right? So X G dash, Y G dash, this product will be what? The product will be XY of G dash, right? This is a definition of product on cosets. Now we know that this is nothing but YX and the commutator of XY. That first property what we approved, right? But these commutators, commutator of XY is already element of G dash, right? So you can write down as YX into G dash. But what does that mean? That means it is the cosets of Y and cosets of X. Okay. So thus G mod G dash is abelian. Okay. So you understood that commutator subgroup or derived subgroup is a character subgroup, and the quotient is always an abelian group. Okay. Clear? So now the most important property we are going to now discuss, and this property is property number 4 probably, yes. What does it tell? It tells that not only is abelian, so G mod G dash is the largest abelian quotient group, quotient of G. What does that mean? That is, if A is an outer subgroup of G and G mod H is abelian, that means this thing, you know, so G mod H is abelian, then this is smaller than G mod G dash. What does that mean? That means G is bigger than G dash, right? Then only G mod G dash is smaller. Then this G dash is sitting inside H. Okay. And also conversely, and also the converse also is also true. The converse is also true. So what does that mean? That means that is, if H is an also group of G and H mod G is abelian. Converse. Yeah. What would be the converse? If yes, so if G dash is sitting inside H for any subgroup H, then H is normal to G and G mod H is abelian. Okay. So first part tells you that if H is normal and G mod is abelian, then G dash is inside H. Conversely, if G dash is inside H, then H is normal to G and the quotient group G mod H is also abelian, right? Now this requires a proper proof because this is a very important idea. The proof is not very difficult. So let us prove the first part first. So what I am assuming that so let H in all subgroup of G and G mod H is abelian. So this is I am assuming. Now I need to prove that I need to prove what? I need to prove that the commuters are inside H, right? So I need to prove what? Need to prove G dash is a subgroup of this, right? This I have to prove. So if I prove that every commuters is element of H, I am done, right? So let me start with commutator. So given a commutator xy, I want to prove this is element of H. So let us find out the cosets of this inside H. Now how the coset look like? The coset will be of the form x inverse, y inverse, x, y, right? Of H. So what does that mean? That means this is of the form x inverse of H, y inverse of H, x H, y H, right? But we also know that H, G mod H is abelian, right? So these elements, they commute each other. So once they commute each other, so what you can do, you can just uh, change those things. So you can write down this YH and then XH. Now you see that these things become identity, right? And once this become identity, then this is also become identity. So it is nothing but 1 of H, right? Clear? As G mod H is abelian. Okay, so what does that mean? That means the cosets of every commutator GH is nothing but equal to H, and this implies that XY belongs to H for all XY belongs to G. Right? For any, if you choose any such things, they belongs to H. So what does that mean? Thus, G dash is a subgroup of H. Okay, so one part is obvious. This is done. Now the second part. Yeah. Conversely, uh, it is given that G is this. This is given, right? So what does that mean? So that means what? That means if you quotient out by okay, but this is a subgroup of this G mod G dash, right? But G mod G dash is always abelian, so this is an always abelian. This is already proved in the last theorem. And H mod G dash is a subgroup of an abelian subgroup, and thus H mod G dash is also abelian. So also normal, right? Because every subgroup of a abelian group is abelian, right? Okay, done. So what does that mean? That means you have a normal subgroup which is normal inside G mod G dash. Now you have that correspondence theorem. By correspondence theorem, what does it tell? It tells that H is a normal subgroup of G, right? Simple. So H is an also subgroup of G, done. And what else I need to prove? So H is an also subgroup of G, and G mod H is abelian, right? Now how to prove G mod H is abelian? So what is G mod H? Now tell me, what is G mod H? Now use the third isomorphism theorem that tells you that G mod H is isomorphic to G mod G dash mod H mod G dash, right? And now this is third isomorphism theorem, right? And you know already this is now subgroup of A, right? So this is abelian groups. You have been all subgroup questioned out by that thing. Then what will be having? So quotient of an abelian group is what? It's always abelian, right? So G mod H is abelian. Clear? Okay, so by this, let me just discuss a little bit about that nilpotent group, how to define it, and then I will finish today's class. So now with the help of this commutator, so we will define something called lower central series. Okay, define. So lower central series. Okay, so how to define it? So first you start with G, or maybe let me see, write down these symbols. Um, uh, G0 is lower, so let me write down by this symbol. G0 equal to G, and then G1 you define the commutator of G and G0. Okay, so G0 equal to G, so this is actually G dash. Okay, similarly G2 you are defining by G with G1 and so on. So in particular Gi plus 1 you are defining by G commutator of G and Gi. Now if you define by this, you see that this will be bigger and this will be smaller than this, right? Commutator subgroup, this will be always, see, H is an out subgroup of H, right? So this will be inside G dash, right? So this will be, so G dash will be bigger, and then G dash G1 and then G2 and then so on, right? And this series is called a lower central series. This series is called a lower central series. Okay. And for nilpotent group, now the theorem is that this series will terminate to the identity. Okay. So theorem. Uh, yeah. So G is nilpotent if and only if uh, this G power C equal to 1 means I mean identity for, yeah, so C is the degree, the class of nilpotency for this, uh, for some, okay, for some C belongs to natural number. Okay, but this C is the class of nilpotency. And the proof is also not difficult. So to prove what you need to prove, so this is proof. So if, so let G is nilpotent if and only, right? So I need to say that first G is nilpotent, then it is true, and if it is true, then G is nilpotent. Now if G is nilpotent, then what happened? Then we know that this Z0 G, which is nothing but equal to identity, and then Z1 G, which is the center, right? And then this series nilpotent of, say, class C. Then ZC of G will be equal to G, right? This is we know. And so now we claim that for any such case you can always find out this lower central series GC minus I minus 1, it will be always inside ZI plus 1 of G into ZI of G. Okay. Into ZI of G, right? The ith centers and I plus centers. So these elements are belong to this, right? What does that mean? That means if this is true, then you know that it will stop, right? So Z0 equal to identity, you know that. So if Z equal to identity, then I equal to 0 means that GC minus 1 will be identity, right? So this will stop, right? Or rather I should say maybe yes. So center. Okay, so how to prove this? When I equal to 0, what do you have? So you'll have no, for let me just prove the for bigger I, right? So for I equal to c minus, so this is true for all I 0 1 to c minus 1. When I equal to c minus 1, then this is z0, which is nothing but g, and this is also um, c minus 1. Okay, so for I equal to 0, you'll have um, for I equal to c minus 1, what you'll have g 0 is sitting inside z of c minus 1 plus 1, so get c of g, and you know that z of g is nothing but g, because g is nilpotent, right? So g0 is also g, right? G is sitting inside g, yeah, so this part is obvious. Okay, so you need to prove okay, c, yeah, c minus 1, okay. So 0 and then c minus 1 will give you 0, yeah, so done. So now how to prove in general? So this is, so if you use induction on this, you will see that both side is true actually. So so now in general what will have, so you have uh, you take commutator subgroup of G to Z I of G. Okay, and I need to, so let me assume that this is true for I or K, and then this has to be, I need to prove it for K plus 1, right? So for K, what happened? Okay, so induction hypothesis tells you that assume that this zk of, for some K, G is nothing but G of C K minus 1, and then Z K plus 1 of G, right? So this is, I am assuming, and then I need to prove that for K plus 1 also it is true. Now for K plus 1 what we will have, so Z uh, okay, so Z um, C K plus 1 minus 1. So what does that mean? That means ZC K minus 2, and ZC K minus 2 should be inside, what should be inside, instead of K it will be K plus 1, say plus 2. Okay, so this will be inside Z of no, I think I need to take the induction of K here. Okay, so yeah, so um, yeah, so this is not the correct thing. Okay, so this is given. Now I need to say, I need to check what, I need to check that Z K plus 1 of G and Z K plus 2 of G, that contains this other part. So what is the other part? So that is, if I put K plus 1, then C minus 1 minus K plus 1, so that becomes ZC minus 1 minus K minus 1, so that means this is GC and K minus 2, right? But what is this? So this is what? So this is GC K minus 2. So you see the definition of the series. See, Z I plus 1 is coming from this. Okay, so this is actually coming from this. So this computer subgroup is nothing but Z C ZC minus 1 minus K minus, right? this is 2, right? And also you note that uh, yeah, so also you note that this the definition of this, so G and for example ZG, what will be the commutators? The commutator will be inside ZG, right? Because this is not sub, right? And similarly G um, into yeah, so yeah, G into Z1 of G, and that will be again inside this is also not sub Z1 of G, but Z1 of G is, yeah, I think there is some, I am missing something here. Okay, which part I am missing? So let me just make it clear. Some part I am missing here. Yeah, so this is equal to this. So now I can replace this series by the commutator, this commutator, right? If I replace by commutator, then what happens? Then it will be of the form uh, Z I plus. This is I need to prove, and this is I have given. This is I have given. This is I need to prove, right? But I know that this is nothing but this, and this is nothing but. So this is nothing but G of G's, right? So let me write down that. So G of ZK plus 1 of G, this is subgroup of this thing is subgroup of um, this is largest abelian quotient, remember. So this is subgroup of JKG, and then you know that this is subgroup of yeah, so this is C K C G C K minus 1, right? But this is K minus 1 is nothing but, it is nothing but G of commutator of G into C K minus 2 by definition of commutators. And then this is also subgroup of um, G, yeah, no, I think the other way. This is, yeah, so Z G K plus 1 of G, and which is nothing but inside G of Z K plus 2 of G. Okay, so this is actually sitting inside these two things, and that implies actually Z K plus 1 of G is actually sitting inside this is sandwich in between this Z K plus 2 of G, this sandwich in between. So if this upper central series terminates, so what is the meaning of that thing? If this upper central series terminates in Cth place, then the lower central series where is the lower central series I defined, yeah, then the lower central series also terminates, okay, because between any two upper central series you have a lower central series element of lower central series sitting there. Similarly, so that gives you that. Similarly, opposite also, between any two lower central series, the upper central, one term of the upper central series is there. So if one series terminates, the other series also terminates, and hence they are equivalent. So saying that upper central series terminates in finite place or lower central series terminates in finite place in identity are same, equivalent. Okay, so this is the basically the proof of nilpotence of some group. Okay. Yeah, maybe if you want, then I can give you a full details proof also, no problem. But I think this proof is fairly enough. Okay, so let me stop here. Okay.